Hi, everyone. This is the Hungry Math Professor here, and I have brought up the continuum hypothesis several times in several videos, which I didn't necessarily plan, but it is a very interesting topic, and so I thought I should explain what the continuum hypothesis is in a little bit more detail, and that involves explaining the cardinality of sets. So in this video, I'm going to explain the cardinality of sets. I'm going to try to do it, though, in the most streamlined way possible. So I just want to say from the very beginning, the sort of completely rigorous way to do this is by talking about bijective functions. And there's nothing wrong with that way. It's actually the correct way to do things. But in this video, I want to avoid a lot of those mathematical technicalities here. And so I'm just going to teach you enough to understand the continuum hypothesis, hopefully show you some beautiful, what I think is beautiful results and ideas. And then if you're still interested, then I can point you to videos where you can learn about bijections and learn how to do this very carefully and rigorously. And it's not just for the sake of carefulness, it also will, you need the bijection concept to be able to talk about sizes of sets beyond just some of the smaller sets, if you will. So I'll say a little bit more about that at the end, but I just wanted to start at that. So in order to do this, I need some definitions of sets. So for instance, I'm going to take the natural numbers and I'm going to do something that some people might find offensive, but for me, the natural numbers will be 1, 2, 3, 4, 5, so on and so forth. I can't list them all out, but the point is hopefully you get the idea. And it keeps going 6, 7, 8, 9, 10, blah, 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 all the way to infinity. This is what I'm going to call the natural numbers. The reason why I say some people say the natural numbers should include 0. I actually don't have a strong opinion on this, whether it should include 0 or not. So um, anyway, sometimes the natural numbers include 0 and sometimes it doesn't. I just need a set, so I'm happy with this for this discussion, and I'm sorry if I bother anybody. But then, we can also talk about what's called set builder notation, where, for instance, if I want to talk about um, the only the even numbers, one way I can do that is to say, okay, look at the set of all numbers of the form 2n, where n is a natural number. So then what is that set? Well, it's the same thing as just taking 2, which is 2 times 1, 4, which is 2 times 2, 6, which is 2 times 3, 8, you get the idea, so on and so forth. So that's a way of describing a set without having to list out the elements. Of course, in this case, I can list out the elements, so I write it in both ways. But this technique is called set builder notation, and it allows us to build sets either when we can't um, list them out, or maybe it's inconvenient to list them out. Okay, so I'm going to use set builder notation from time to time, and again, it's whatever before the colon is giving you a description of what's in the set, and then to the right, it's also giving you a description of what that means, right? So again, the way you read this is the set of all values that are written as 2n, such that n is a natural number. Okay, great. So what are some other sets that we want to be able to work with? There's something called the integers, and I will list them out, but I need a doubly infinite list now. So it starts from negative infinity to 0, and then counts up to positive infinity. So um, all the negative whole numbers, 0, and all the positive whole numbers here. And so this is the integers. Maybe I'll write that on the side. So this is the natural numbers. And this is the integers. And what else can I do here? Some sets that one more set that we need for sure is the rationals. So this one I don't want to list out. So it's going to be the set of all numbers of the form p over Q, where P and Q are in the integers. So I'm using some notation you might not be familiar with, but this says P and Q are in the integers, meaning P and Q are both integers. I just have to exclude the possibility that Q could be 0. If I do that, I get the rational numbers. Okay, and then of course, when I define the rational numbers, I'm assuming some things about how to add and multiply and divide fractions such that, and also what two fractions are the same. So of course, 4/8 is the same thing as a half, which is I'm using that and not sort of defining that too carefully here, but that's sort of in the background as an assumption. Okay, what else do we need? Well, one more set I want to introduce because it'll be an important example is natural numbers cross the natural numbers, okay? I'll draw this when we get to this example later, but I just want to introduce it now. So this is, forgive me for my triple equals here. So this is the set of all pairs of natural numbers, where n and m are both natural numbers. So we're talking about, an example of this kind of thing is like 1, 4, or negative, nope, not negative, sorry, 3, 7, 1, 1, and so on and so forth. Okay, so there's some examples of sets, and now I want to talk about sizes of sets. Now, first of all, if you've never seen this before, that might kind of seem bizarre, right? Because all these sets so far are infinite, right? They're just infinite sets. They have infinite elements in them. So shouldn't you just say the size is infinite? And there's a natural intuition to that. You're not sort of crazy to think that way. That was sort of how I think a lot of mathematicians in the history of mathematics would have thought of it. But it turns out that George Cantor came along and came up with a way of distinguishing different sizes of infinity, and we haven't looked back since. Though at the time it was like very kind of revolutionary, but now we have fully embraced this and understand that this is definitely correct. So I'm going to try to give you an idea of how that could be, right? Now, the analogy is like following, right? If I give you just two finite sets, right? Let's say I give you the set 1, 2, 3. And then I give you the set A, B, C. Great, right? So let's just draw a simple little silly picture here. And then over here, similar kind of thing. A lot of times we like to draw sets with just like little blobs, like little bags containing these points. Yeah. Now, because they're both finite sets, if I asked you, are they the same size? You probably just count both sets and say, yeah, the first one has 3 elements, the second one has 3 elements, so they're the same size. And that's a completely reasonable thing to do. But if you couldn't count them, then let's say you couldn't count to 3, right? Which is a weird thing to say, I get it. But let's say you couldn't count to 3 for some reason, and I asked you for some other way to do this. Well, another thing you could do is just to pair them up. You'd say, okay, well, let's pair this guy with this guy with that guy, and that guy with that guy. I don't need to be able to count in order to do that. I can just pair things up. And I say, oh, they're the same size because everybody on the left has a pair with somebody on the right. Right? Now, this is important, and this is like an important thing that happens in mathematics where, we know how to count, so we just count things. But then when we need to go to something more abstract or more complicated, like infinite sets, if we count, we're always going to get infinity. So that's not really going to work. So instead, we try to line them up like this. This is where we call this a one-to-one correspondence or a bijection. So one-to-one correspondence, or we set up a bijection. And this is where I'm going to hide all those details. But if you want to later sort of dive into those details, I can point you to where to do that. But I want to hide a lot of the more complicated machinery in this first video, so I can just kind of show you the pretty stuff and hopefully inspire you, and then inspire you to want to dig into some more of the details later. Okay, so we're going to avoid bijective functions here, but there's still a reasonable way to talk about a one-to-one correspondence. Okay, so before I get into that example, let me just make a definition, and then I'm going to do several examples. So definition, we say an infinite set S, so S could be any of the sets I just gave you, for example. We say an infinite set S is countable if the elements can be listed out starting from 1, 1, 5, 1. Now, let me just be clear. In this video, I'm not being super rigorous, so even the language I'm using in this definition is a little vague. I'm going to do that in this video because I think it'll give us the idea. I'm going to do examples. You'll understand what I'm getting at. But just because I know mathematicians can be love to get frustrated with this kind of thing, I need to at least say that so that we don't get frustrated. So there's a more rigorous way of saying what I'm saying right now. Okay, but I'm going to show you what this means more carefully with examples in a second. And so in this case, we say that the size of S, so we use these absolute values for the size of S, is the same as the size of the natural numbers. Okay, otherwise, so if that's not the case, then we say that S is uncountable. Okay, so those are the two options for this video. We'll just going to look at those two options of being countable or uncountable. And this is the sort of rough definition that I'm going to use, which will be completely reasonable for what we're doing in this video. So in order to understand what I'm talking about, though, I need to do some examples. Okay, so first of all, let's do this example, which is to show that the natural numbers have the same size as even natural numbers. Okay, so the even natural numbers, I defined it earlier, but I didn't use this notation 2 times n. These are the guys 2 times n, where n is a natural, right? So it's a set of all numbers which can be written in the form 2 times n, where n is a natural number. Those are just the even natural numbers. Okay, so when I say that it needs to be listed out one by one, what do I mean is the following. So I'm going to put slots, the first slot, then the second slot, the third slot, fourth slot, fifth slot, so on and so forth. So this is what I mean when I say if the elements can be listed out, maybe I should say elements can be listed out starting from 1. So I started from 1 and I go one by one, right? So I'm just adding 1 every time. That's what I'm saying in that sort of not so rigorous definition. And so I need to be able to list them out. But right now in yellow, I'm just listing out the natural numbers, right? So in order for them to be the same size, now I have to list out these guys, the even natural numbers, and then they'll be the same size. So for 1, its buddy is going to be 2. For 2, its buddy is going to be 4. For 3, its buddy is going to be 6, 8, 10, 12, 14, so on and so forth. And so just like we did with the silly example with 1, 2, 3 and ABC, we put each member of the first set into one-to-one correspondence with the member of the second set. Here we can do the same thing with the even natural numbers. They can be put into one-to-one correspondence with the natural numbers in this very natural way. So they have the same size. Now that already should, if you're not used to this, that already should feel bizarre. Like, what's going on here? You know, it feels like there's half as many numbers in the even naturals as there are in the regular naturals, right? Somehow I got rid of half of them, but yet the size is the same. right? And that's what it's bizarre things happen in infinite sets like this. And I'm gonna blow your mind even more if you find this already surprising. They can't do that with finite sets though, right? If you take a set of size 6 and then you throw away half of them, you're gonna get a set of size 3, right? So you know you can't do such bizarre things with finite sets, but it turns out with infinite sets, there's going to be a lot that can surprise us, right? So right away, the first example is that the even numbers, with natural numbers, which again seem to be half as big, are actually the same size of infinity. Okay, they're both what we call countable. All right, well, we need to see some more examples. So let's see, what's next? Well, next I'm going to show that the size of the naturals is actually the same as the size of the integers. Okay, remember that the integers are set -3, -2, -1, 0, 1, 2, 3, so on and so forth. Now here you might feel like, hey, the integers are like twice as big as the naturals, right? Somehow that's this sort of intuition that you have. This is the thing with intuition in mathematics is that when you're doing something new, your intuition is often off. You don't have any intuition for infinite sets, so your natural intuition is just not necessarily very good, right? It does feel like the integers are twice as big as the natural numbers in some sense, but it turns out that if what you mean by size is that they can be put into one-to-one correspondence, they're going to be the same size. So how do I do that? How do we do that, right? So I have to come up with some way of taking this set and listing it out one by one, starting at 1. Okay, so I'm going to just start by listing 0 first. Then I'm going to list 1. Then I'm going to list -1. I'm going to list 2. Then I'm going to list -2. 3, -3, so on and so forth. And you kind of zipper them together, right? So again, the integers feel twice as big. How are you going to fix that? Well, you just kind of zipper the right side that goes to positive infinity and the left side that goes to negative infinity, zipper them together in this way, and you can list them all out, right? And so if this is what it means to have the same size of infinity, then they are the same size, right? I can put the integers in one-to-one correspondence with the natural numbers. So they have the same size. You should just think about the fact here. So again, to make this completely rigorous, you define a bijection between the natural numbers and integers. Here, in order to just be careful, we should just kind of think a little bit longer to make sure we say, oh yeah, every integer is going to show up if I keep going like this, right? And you can check that for yourself. It's definitely the case. Okay, so there are 2 examples so far. Let's hopefully I've surprised you a little bit because I think being surprised in mathematics is when we get inspired, when we feel like some passion towards the subject. So I hope I've surprised you at least a little bit so far. And I'm going to keep surprising you hopefully as the video goes on because I've saved the best for last, if you will, and they're going to just increase in their weirdness or their unexpectedness. So here's the next example. So now the natural numbers have the same size as the natural numbers cross the natural numbers. Now again, that feels a little bit weird. Sorry, this triple equals keeps coming up here. Um, that doesn't seem right if you're not used to this. Remember what the natural numbers cross the natural numbers are. Um, they are the set of all pairs n comma m, where both n and m are naturals. And just to try to understand this set a little bit better, I will draw it for you. So if we are in the xy plane, I only need the positive xy part, so I'll just draw the positive axes here. Then what are we talking about, right? So let me draw a different color. So we're talking about 1 comma 1, so that's like 1 comma 1, right? 1 comma 2, 1 comma 3, 1 comma 4, 1 comma 5. Then we go up, so on and so forth. These are set of all ordered pairs with natural number um, entries. Okay. Now this set, your intuition, if I am a good guess for what your intuition is saying, this set feels a lot bigger than the natural numbers, right? I mean, it's almost like we multiply the natural numbers times the natural numbers. That should be a lot bigger in size, right? Certainly, if you do this with sets, finite sets, you're going to get something like if you take a set of size 5 and then multiply it by a set of 5, you're going to get a set of size 25, right? But in this case, I'm claiming already that they're the same size. Okay, so somehow um, I need to be able to put them in one-to-one correspondence with the naturals, right? So again, I'm going to start my list. One, two. I need to give myself more room. Sorry. Let's. So I'm going to start 1, 2, 3, 4, 5, 6, 7, 8, 9, and that'll be enough. All right. So the question is, how are we going to do this? How are we going to put them in one-to-one correspondence, right? So I'm going to start with 1, comma 1. All right. Nothing. That doesn't really get the trick at all, but that's where I'm going to start. All right. We start with 1, comma 1. And let me just label a few more of these first. So then let's see. This is 2, comma 1, and this is 1, comma 2. Then we have 3, comma 1. We have 2, comma 2, and 1, comma 3. Okay, and the trick here is to, I kind of already alluded to it, but the trick is to follow these kinds of grid lines here. So I'm going to start one like this. Okay, so then if I follow these guys, I'll be able to list them out. So I'm just going to follow these diagonal lines. And notice any diagonal line that I draw is only going to have finitely many of these yellow points on it. So I'm not going to run into like one of these red lines that has infinite many of these yellow points, which would be a problem. Each one's going to be has finitely many, and then I could just keep stepping through this process, right? So the picture's going to get a little ugly if I keep going too much. But that's how I'm going to list them out. So first of all, I get 1, comma 1, then 2, comma 1, then 1, comma 2, then 3, comma 1, then 2, comma 2, then 1, comma 3. Then I didn't give myself enough points here in the actual list, but that'll be 4, comma 1, then it would be 3, comma 2, and then it would be 2, comma 3. Okay, and then so on and so forth. All right, so that shows that they're the same size. You just have to, in order to be careful, you have to notice that you'd never double count a green, you'd never double count one of these ordered pairs doing this because you're never going to double back and come back to one of these diagonal lines. And if you keep drawing these diagonal lines, you'll eventually hit everything in the ordered pairs n cross n here. So we are going to get everything. And again, we can do this with bijective functions later, but for now, we see that, yeah, they are the same size. I mean, it's weird and it's surprising, but apparently they are the same size. So we have to accept it, and it's pretty nice. Um, I won't actually do this for you, but I want to just uh, allude to the fact, or just say that it actually doesn't matter how many times you cross here. So if you take the natural numbers, will have the same size as the natural numbers cross the natural numbers cross as many times as you want. Oops. So here, where we're doing this n times. So that would be like, instead of ordered pairs, you'd have ordered n tuples, we call these things. So like, for instance, could be something like 1, comma 2, comma 5, comma 1, comma 7, comma 8, whatever, which is bizarre, right? Again, I'm not going to show you the proof of that, or give you an idea of it even, but I just wanted to mention it as like an extension of the previous example. Doesn't matter how many times you do this, they'll have the same size as the natural numbers, which is, again, really surprising because this set on the right feels a whole lot bigger. But again, if your notion of size is to be able to list it out, then turns out they're not bigger. All right. So hopefully so far you're enjoying this. It's kind of messing with your head a little bit. That's what I want. I think that's part of what makes learning advanced math topics fun is that there's a lot of wonder and curiosity that comes with exploring things that just feel completely unintuitive at first. So let's do another example. Now this one is quite surprising as well. So here we say that the natural numbers, turns out, have the same size as the rationals. Now that's also quite bizarre. So the rationals, again, are the set of all fractions, right? That's what we said before. Let me just be a little bit more careful. So we're talking about P over Q, where P and Q are both integers, and Q, you're not allowed to divide by 0. Okay, so apparently they have the same size. And I'm going to give you the idea here, but in order to do that, let me do let me define two more things. So I'm going to define what we call the negative rationals and the positive rationals. So the negative rationals are just the set of all, I don't know what letter to use here. Let's just say the set of all, maybe that's confusing though to some people. Um, let's just say the set of all um, L here, such that L is strictly positive. Sorry, I did that backwards. Strictly negative. And here is the set of all fractions which are positive. So I'm just breaking out the positive fractions and the negative fractions. And so I can write the rationals in the following way, which is Q minus union, the set containing 0, union, the set containing the positive rationals. Now, if you've never seen union before, this is not a very difficult concept. It's just saying take the set Q minus, adjoin to it the element 0, and then adjoin to it all the positive rationals. So the rational numbers are just all the negative rationals plus 0 plus all the positive rationals, right? Well, that's pretty intuitive, right? Okay, good. So what we're going to actually do is, so we will show that the positive rationals have the same size as the naturals. That's actually what I'm going to show you in a picture, in a sort of intuitive kind of way. And that's enough. So notice this is enough by considering the argument we used to show that the naturals have the same size as the integers. Okay, so we don't have to worry about this. We're just going to show that the positive fractions have the same size as the natural numbers, and then we can do the same zippering technique that we did for the integers to show that the rationals have the same size as the naturals as well, which is what I'm talking about here in this note, because that's how we showed that the naturals have the same size as the integers. We just kind of zippered them together. Okay, so again, what we're going to actually do is show this, or what I'm actually going to show you is this. Okay, and I'm going to do this with a picture, right? So again, this is all just, we're focusing on intuitive things here. I don't want to get bogged down in the details in this particular video. So how do we do this? Yeah. So we're going to build this table. All right. So what's the table look like? Well, it's going to look like this. Okay. And at the top, we're going to have the numerator, and the bottom, we're going to have the denominator. You'll see what I mean in a second. Okay, so the numerator could be 1, 2, could be 3, could be 4. I don't want to get too crazy. filling out this table. Let's go to 7. 1, 2, 3, 4, 5, 6, 7. Stop there. This is already going to get a little crazy. So, and I need a little bit of graph paper, if you will. So I'm going to fill out this table a little bit more. And, I'm just going to make a table of fractions, basically. All right, so what does my table of fractions look like? Well, let's use a different color. And so this will be like 1 over 1, yeah? And this is like 2 over 1. This is like 3 over 1, 4 over 1, 5 over 1, 6 over 1, 7 over 1, so on and forth, so forth. So now this is like 1/2, this is like 1/3, 1/4, 1/5, 1/6, 1/7. And anyway, I'm going to keep filling this out, but make sure I don't make a mistake. All right, so again, we're just filling out this table exactly as you would expect, I hope. That's what I get for trying to go fast. 5 halves, 6 halves, 7 halves. Here I go. Okay, so you should start wondering, like, how are we going to use this to list out these guys, right? But first of all, before you do that, can you convince yourself that every positive fraction is going to occur in this list? Can you convince yourself of that? I'll let you think about it as I'm filling out this tediously long table here. So can you convince yourself that every positive fraction is going to occur, in this list? And if you think you can, give me an argument. What's the argument for it? Shouldn't have went all the way to 7. But we're almost there now. So what's the argument that every positive fraction can show up in this list? Yeah, well, the idea is just that any positive fraction is going to have a numerator, denominator, and the numerator can be some positive natural number, and the denominator can be some positive natural number, right? So by definition, this is going to be every single fraction. Now, that being said, there's going to be duplicates. I mean, we can already look at this and see there's lots of duplicates, like 1 over 1, 2 over 2, 3 over 3, 4 over 4. I mean, those are all duplicates, right? So we are going to list out every positive rational number this way, but we're going to get a lot of duplicates. So what the heck's going on, right? How are we going to do this? Okay, well, again, our goal is to show that the rationals can be listed out. So let me put my little template down here. If this is going to work, I need to be able to list these guys out somehow. So that means I need to start at 1 and list them out one by one. All right, great. So how are we going to do that? Well, we're going to do something similar to what we did when we looked at the ordered pairs of natural numbers. So we're going to start going through this list in this sort of diagonal way. And so the first guy is going to be 1 over 1, which I'll just write as 1. And the difference, well, let's keep going, and then I'll point that out in a sec. So then we keep doing this, yeah. So now the next guy is a half, and then 2 over 1, which I'll write as 2. Now we go to the next guy. Okay, so now that's a third. Now, hold on a second, because the next guy in this list would be 1. Okay, so I forget about that because I've already listed it. So I'm not going to list it again. All right, so I've already listed 1, so I skipped that guy. And then the next one is 3, and I haven't listed that yet. All right, so now I keep going, right? And so the next guy is a quarter. That's a new one. Then 2/3, that's also new. Then 3 halves is also new. And then 4 is also new. So now we go to the next one. Okay, so now 1/5 is new. But notice that 2/4 is not new, so we skip it. 3/3 is not new, that's just 1. And 4/2 is just 2, so we skip that. And the next guy would be 5. I didn't give myself the next one. But the point is that you can keep doing this, right? So now we can follow this next row. And again, let's see, is there any duplicates in this row? I don't think so. This one will all be new, I believe. But eventually, like when we get to the next one, there are going to be several duplicates and we'll just skip them, right? So this guy's a third, so we skip that. This guy is just 1, so we skip that. This guy is 3, so we skip that. So the point is that it's a slightly different algorithm here. We're going to follow this list. Every single time we draw one of these diagonal lines, there's only going to be finitely many fractions on it. So we're never going to get into some, infinite subroutine or anything like that. But the difference is just anytime we find something we've already put in our list, we just skip over it. Perfectly reasonable thing to do. And that means that when I list them out, I'll never double up a fraction that was already in the list. Okay, I don't want to double up a fraction that was already in the list. That's what we call one-to-one correspondence, which again can be made rigorous using the idea of bijections. But here, if I do this and keep following this procedure, I will eventually list out every single positive rational number. I mean, it's not a very pretty list in the sense that, like, I don't know that I want to list it out this way. That's why I use set builder notation like normally, but it is a completely reasonable list that I can make. So that means that the positive rationals have the same size as the regular natural numbers. So let's just follow this up with a little bit here. So that says that the natural numbers have the same size as the positive rationals, but nothing we just did really had anything to do with the positive rationals. So they have the same size as the negative rationals. And, we said earlier, by doing this kind of zippering technique like we did with the integers, we can show. So we can show further that the naturals have the same size as the entire rationals. Okay, I won't do the zippering here, but it's completely similar to what we did for the integers. Now that you know that you can list out the positive rationals, you can list out the negative rationals. There's a pretty clear correspondence between the integers and the rationals now, and then you can use that same procedure to go from the integers to the naturals. Okay, so now, so far, everything I've shown you is an infinite set, which has the same size as the naturals. If every infinite set had the same size as the naturals, this would be a complete waste of time because we already knew that. Every set is infinite. I don't need this bizarre way of saying that they're infinite. Yeah. So so far, you might start to feel like this is getting silly, right? If you're just going to list every single infinite set out, so what? And so I need to show you that that's not the case. There are sets which are not countable. And there's sets that you're already kind of familiar with, which are not countable. So what's the set that I need here? I haven't talked about the real numbers yet. Again, I don't want to give like a very formal definition of the real numbers, but I'll just use your intuition here. So this is the real numbers, which are, informally the set of all decimals. Okay, and let's just leave it at that for this talk. But these are things you've encountered before. So every rational number is a fraction which can be written as a decimal. So every rational number is a decimal, but there's also things like square root of 2, square root of 5, all the square roots, all the any roots really are in here, and then you have pi, which is we know that can be written as a decimal, and e, and all kinds of different numbers like that, right? So anything that can be written as a decimal is in the real numbers. Okay, and so what we're going to show is that so the example is going to be that there's a couple of ways I can write this. So the real numbers are strictly bigger than the natural numbers, or in the way that we said this before, R is an uncountable set. See, here you see why the name uncountable is good, because if you can list out the elements, then you can sort of count them one by one, right? So if you cannot list them out, then we say it's uncountable. There's no way to count them, right? That's sort of the idea behind this name. All right, so I want to show you, this is a difficult proof. I'm gonna go for it. So hold on to your seats. This is going to be the most technical part of what we do. Um, but in order to show you this, I will cheat a little bit. So I'm going to look specifically at the interval 0 to 1. Okay, so this is the set of all x, which are real numbers, so that 0 is less than x is less than 1. So on a number line, this is if we look at the real numbers as a number line, we're just looking at the guys that are between 0 and 1, not including 0 or 1. So I'm talking about all the numbers between there. As decimals, that means they look like, 0.1, 2, 3, 1, 7, something like that. Dot, dot, dot. They're never going to have a number to the left of the decimal because they're between 0 and 1. And so any fraction which has 1 in the numerator, for instance, or it doesn't have to just have 1 in the numerator, but any fraction where the numerator is smaller than the denominator is what I should say, then that's in this set. But then just any decimal that's doesn't have anything to the left here will be in this set as well. So we're going to show, so we will actually show that the size of just this piece of the real numbers is strictly bigger than the naturals. And hence, just the interval from 0 to 1, the open interval from 0 to 1 is uncountable. And then I'm going to let you, again, we can do this all very carefully, but I'm just going to let you hopefully buy with me here that if the open interval from 0 to 1 is uncountable and the real numbers are certainly bigger than that, then the real numbers are also uncountable. So I'll let you just buy that intuition. It turns out that intuition is correct. There's a way to make that rigorous. So here I'm just going to show this other fact, which is a little bit easier to show in a proof and without using bijective functions. Okay, so we're going to do the proof even. So let's get ready for that, right? So how does this proof work out? Well, we got to do what's called a proof by contradiction. Okay, so what we're going to do, we're going to say, well, for sake of contradiction, meaning I'm about to make an assumption that I expect to be incorrect. Okay, so I'm going to make this assumption hoping that I eventually lead to a contradiction, and hence the opposite of what I say must actually be true. So for sake of contradiction, assume that the set is countable. Right? And hence, we can list out all the elements in decimal notation. Okay, so what do I mean by that? So let's draw a little bit of a table here. So I'll list out 1, 2, 3, 4, 5, 6, 7, then I'll have to stop there. So I want to list out all these guys. So the first decimal in my list, I don't know what it is. So I'm just going to write it like this. It's going to be, the first number could be A11, the second number could be A12, third number A13, A14, dot, dot, dot. The second fraction, the second decimal is like A21, A22, A23, A24, blah, blah, blah. The third one, A31, A32, A33, A34. And again, I've made a list that's probably longer than I need, but Just bear with me for a second. The point here, though, is that I'm assuming that these guys can be listed. So that means, I could just put them in a list like I'm doing now, but they're decimals and they could involve sort of, they could be every single one of these decimal places could be non-zero. So I need, they could be infinitely long all the time, and I need to list them out like this. And the thing is, I don't actually know what the list looks like because I'm actually thinking that the list cannot possibly exist. So that's why this gets a little more complicated for students. I've noticed it just looks really complicated to list out all these variables. Like, what the heck is he talking about? There's so many letters here, right? That's just how math goes, though, eventually. So I'm not gonna, nothing I can do about that per se. But the point is that every single decimal we're assuming can be listed out one after another, starting at one. And every single one of these guys is supposed to be unique. Okay. So where each a sub ij, these elements which are decimals, um, are in the set, well, they can be 0, 1, 2, 3, 4, 5, 6, 7, 8, or 9, right? This just how you write decimals, right? So for example, just in case this is really bothering you, like one example could be 0.257314, I don't know, keeps going, right? That's like one of these numbers could look like that. And all of them look something like that. But again, I can't say anything more than just, if I'm going to list all the decimals out, they look something like this, where each a sub ij is just a number between 0 and 9, which is the decimal place, right, for that particular decimal. Okay, so now what are we going to do? How is this proof going to go? So now we will write down a number. Let me just say it differently. Let me say a decimal. So it's going to be a decimal that we know is in here. Sorry, let me say this. A decimal in this set that we supposedly listed out, which cannot be in the list. Okay, and if we can write out even just one decimal, which we know is in this set, the open interval 0 to 1, which is not in the list, and we get a contradiction because we assumed we wrote down the entire set in our list. Okay, so how are we going to do this? Let me get a different color. This is called Cantor's diagonalization argument, because now we're going to look at this diagonal. I should have made the list a little bit longer in the other direction, I guess, but we're going to look at this diagonal where every single element I look at is always going to be of the form a sub the same number twice, right? So a sub 1, 1, a sub 2, 2, a sub 3, 3, so on and so forth. And I'm going to change that number slightly when I go to write B. So let me say this down here. So this chosen number will be of the form. So let's just call it B, which is going to be a decimal written as, just to use the same notation as above, 0.B1, the first decimal place, D2, B3, B4, B5. I shouldn't have put the comma. So it's going to be another decimal. So that's why I know it's going to be in the open interval from 0 to 1. And, where each B sub I is in just, exactly what you expect. But now I have to tell you how to pick each of these decimal places, right? So how the heck do we do that, right? So to be more precise, whoops. So to be more precise, we choose BI as follows. So what's BI? So BI will be equal to 1 if the diagonal element a sub I is not equal to 1, and it'll be 2 if a sub I is equal to 1. Yeah. So let's do a little example of what the heck's going on here, right? So let's do this in a color. So if a sub 4 is equal to 3, then b sub 4 is equal to, well, it's not equal to 1, so b sub 4 is equal to 1. Okay. And so if a sub 7 is equal to 1, then b sub 7 is equal to 2. But the point is that we've set it up so that the fourth digit of b will never be equal to the 4 digit of the fourth digit of the fourth number, right? And the seventh digit of b will never be equal to the seventh digit of the seventh number, and so on and so forth. So just to go back to the table above for a second, that means that the first digit of b will never be equal to the first digit of the first number. The second digit of b will never be equal to the second digit of the second number, and so on and so forth. The 100th digit of b will never be equal to the 100th digit of the 100th number. And so another way of saying this symbolically is that uh, you know, by definition, b sub I cannot equal a sub I. Again, the ith digit of b cannot be equal to the ith digit of the ith number in the list. But this implies that b cannot be equal to any number in our list. That deserves an exclamation point. So that's a contradiction. But it can't be in the list because it always differs from every number in the list. It differs at least in one digit. And as soon as one digit differs, it's a different real number, right? It's a different decimal. So the conclusion then, because you assume for sake of contradiction that you could list out the elements, you went through this argument and you found out that there was a contradiction. So that means, hence, the elements of 0, 1 cannot be listed out. So 0, 1 is uncountable. Okay, cool. I love this argument. This is called Cantor's diagonalization argument. It turns out there's more Cantor's diagonalization arguments get used all over set theory and lots of different areas of mathematics for all kinds of different things. So this is a very important example of an argument that gets used all over the place, but it's also just a really pretty argument. It's quite difficult if you've never seen it before, so you might need to kind of slow the video down and watch it again, or ask some questions or something. But now, again, I said this earlier, now we also know, furthermore, that the real numbers are also uncountable. So that's also a fact that we can do. So now I want to state the continuum hypothesis. So what is the continuum hypothesis? So the continuum, because this raises a natural question. At first, I showed you a bunch of examples of infinite sets, and they all had the same size as the natural numbers. So it was quite surprising, but eventually we started to see a pattern. But now I've shown you that, okay, not every infinite set has the same size. The real numbers, a very important infinite set, is strictly bigger than the natural numbers. And maybe I should just mention at this point that the complex numbers are also strictly bigger than the natural numbers, but the complex numbers have the same size as the rationals. Just to show you another example without any justification or anything like that. Complex numbers, of course, when you take a plus bi, where I is the square root of -1. Okay, so there's so many different infinite sets. If you study set theory, there's a whole hierarchy of these ordinal numbers and cardinal numbers, and lots of great stuff to play with there. There's something called power sets, which let us get larger and larger sets, and I might do a video on that at some point. But there's a natural question without having to go all the way to this power sets and all this crazy stuff. There's a very natural question already that's stuck to it. So the real numbers are strictly bigger than natural numbers. So here's the continuum hypothesis. Is there I'm going to state it as a question. So is there a set S so that the following occurs? So that the natural numbers are strict, sorry, one thing I want to say, well, let me leave it like this is fine. So, but you should think of S as a subset of the real numbers. So, but I want to know, is there some subset? It doesn't actually have to be a subset, but is there some subset so that its size is strictly between the natural numbers and the real numbers? Okay, so this is a question you can ask. It's a very natural question. Continuum hypothesis. Okay, now what's interesting about the continuum hypothesis is, well, no one's proved it yet, right? But it turns out that what we have proved about it is that you cannot prove it, which is quite bizarre. So we know that, oh no, sorry. We know that, so we know that so this is abbreviated CH often. The continuum hypothesis cannot be proven true or proven false from the axioms of what's called ZFC set theory. That is just the accepted foundation for mathematics at the moment. So this is the typical foundation that's given for mathematics. People can argue about what the right foundation should be in philosophy and set theory and things, but this is the established sort of orthodoxy of what the foundation should be. And what's interesting is that this tells us that it's not so much that we just haven't worked hard enough or we haven't tried hard enough to prove the continuum hypothesis. This means that you cannot prove the continuum hypothesis to be true and you cannot prove it to be false. So we say that it's independent of the axioms of set theory, of ZFC set theory. What an interesting result, right? That's so profoundly interesting. This was shown, one side of this was shown by Gödel, the other side by Cohen, and it's turned into this huge area of machinery for talking about sizes of sets and showing that axioms are independent of set theory. There's many, many different things that are independent of set theory. Going back to Gödel's incompleteness theorem, here's an example of a statement, which is a very natural statement that can be made about mathematical objects. Is there any subset of the real numbers whose size is strictly between the naturals and the reals? Pretty natural mathematical question, and it's undecidable, right? So another way of saying this is that CH is undecidable. So it's an example of a mathematical fact which cannot be decided, which is what Gödel's incompleteness theorem says is always true of any system of axioms which can express number theory. So the question is then, this is kind of bizarre. It feels like from a mathematician's point of view, there should be some answer to this question. This is a very natural question about the real numbers. There should be some answer. Um, so there's different philosophies here. Some people say, yeah, there should be an answer to the continuum hypothesis. So we have to just keep investigating and looking for natural axioms to add to Z of C that would tell us whether the continuum hypothesis is true or not. And I can't do too sophisticated of a discussion of that here, but I'm just going to leave it there. Some people say, hey, yeah, there's definitely an answer to this question. We just need to add more axioms to Z of C and we'll figure it out. Okay? There's some problems with that, but I'll leave it there. And other people like Joel David Hampkins, which I've talked a little bit about on this channel, he argues that actually there's this whole multiverse of different set theories. And depending on which universe of set theory you're in some universes, the continuum hypothesis is true, and in some universes, it's false. And that just is what it is. And so we need to embrace this sort of multiverse of different set theories. And that is how we answer the continuum hypothesis. We just answer it relative to whatever universe we're in, right? So I'm going to leave it there. I'll probably do some other videos where I discuss more of this philosophy in more detail. But here I just wanted to kind of leave you with some awe and wonder. I hope you enjoyed this little discussion of introducing cardinality of sets and showing some deep things here at the end. If you find this really interesting and you want to go further, you need to learn about bijections of functions so that you can look at sizes of sets that are bigger than the real numbers and talk about power sets. And we can show that there's actually a whole hierarchy of different sizes of sets. There's infinite sizes of sets basically. So I'll do a video on that as well later. But for now, I hope you enjoyed this. Like, comment, and subscribe. And I hope to see you at another one of my videos. Thanks.